Hello everyone, my name is Richard McKee and I'm a senior mechanical engineering major at North Carolina Agriculture and Technology State University in Greensboro, North Carolina. Today I will be discussing a method to control the Denso VP6242-G 6 degree of freedom robotic arm in Figure 7 using the Microsoft Kinect infrared sensor version 2 seen in Figure 5. Applications include space exploration, advanced manufacturing, work in extreme environments, and telesurgery. Currently, there are several ways to control a robotic arm: a joystick, programming waypoints, and even virtual reality interfaces. The Microsoft infrared sensor assigns points to different parts of the body. The X, Y, and Z coordinates for each point are stored in an array that can be accessed in MATLAB. However, before using the information stored in the array, the difference in the X, Y, and Z frame of the Denso and the X, Y, and Z frame of the Kinect must be considered. The limitations of joint angles are listed in Figure 8. This becomes important when considering solutions for desired path for the arm, as well as protecting the robotic arm from damage. The emergency stop button seen in Figure 2 was used to stop the arm if it became erratic. A problem arises when you consider that there are two configuration spaces, one for the Kinect and one for the Denso robotic arm. In order for this interface to work properly, the relationship between a change in position of the user's arm detected by the Kinect and the motion of the robotic arm must be established. Code is written in MATLAB to make the configuration spaces compatible. As you can see in figures 11 and 14, the Z direction for the Kinect is back and forth, whereas the Z direction for the base frame of the Denso is up and down. There are multiple ways to solve this problem. The first is by using DH parameters. DH parameters are used to create a transformation matrix that relates the base frame with the end effector. Figure 3 shows how DH parameters are found. As the arm moves, the sudden changes from waypoint to waypoint can cause instability in the system. To create a smooth path, a parametric curve between the points is used rather than a linear path, outlined in Figure 4. MATLAB simulations are used to test how the robotic arm responds to the real-time X, Y, and Z coordinate data coming from the Kinect sensor. In order to do this, a rigid body tree is required. The rigid body tree may be created from the DH parameters in MATLAB or imported using a SolidWorks model. The latter is chosen for this project. A SolidWorks model, in Figure 10, of the Denso robotic arm allows a URDF file to be exported. The URDF provides MATLAB the information needed to create a rigid body tree. The rigid body tree, seen in Figure 12, allows each frame of the joint to be represented within MATLAB. A challenge that was overcome during this research was getting two Simulink models to run simultaneously. This was accomplished by using a TCP IP block within Simulink. One issue with optimizing this design was the difference in frame rates between the Denso's fixed 1 kHz sample rate and the 30 frames a second Kinect frame rate. Further research is needed to overcome this issue, but the results from this experiment will allow compatibility between the Denso VP6242-G 6 degree of freedom robotic arm and the Microsoft Kinect infrared sensor. Special thanks to North Carolina Agriculture and Technology State University, Dr. Soni, and the U.S. Department of Education for making this opportunity possible. Thank you.